In the winter of 1961, a scientist stopped for a cup of coffee and accidentally broke one of humanity's oldest dreams. The dream that if we were only smart enough, we could predict the future. His name was Edward Lorenz, and the tiny thing he noticed that morning would grow into one of the most unsettling and beautiful ideas in all of science. We call it the butterfly effect, and almost everything you think you know about it is slightly wrong. For 300 years, science ran on a single confident promise. Isaac Newton had handed us laws of motion so precise that we could predict eclipses centuries in advance, steer planets across the sky, and time the return of comets to the day. In 1814, the French mathematician Pierre-Simon Laplace pushed that promise to its limit. He imagined a vast intellect that knew the exact position and speed of every particle in the universe. To such a mind, he wrote, nothing would be uncertain. The future, like the past, would be laid out in full view. This idea became known as Laplace's demon, and for over a century it was the quiet faith of science. The universe was a clock. Wind it up, know the parts, and the future is yours. Edward Lorenz was a meteorologist at the Massachusetts Institute of Technology, and he had built a small mathematical universe to test that faith. It was a stripped-down model of the weather, just 12 equations running on a primitive machine called the Royal McBee, a computer slower than a modern pocket calculator that filled half a room. Each run printed out columns of numbers, the rising and falling of an imaginary atmosphere. One day, Lorenz wanted to look again at a sequence, so instead of starting from the beginning, he took a shortcut. He read a number off an earlier printout and typed it back in. The number he entered was 0.506, but the number the computer had actually been using was 0.506127. He had dropped the final digits, a difference of about 1 part in 1,000, a rounding error so small it seemed beneath notice. Then he walked down the hall for coffee. When he came back, the weather had gone insane. The new run started out matching the old one almost perfectly. But the two slowly drifted apart, then split, then diverged so completely that within what amounted to about 2 months of imaginary weather, they had nothing in common at all. Two nearly identical starting points had grown into two utterly different worlds. Lorenz stared at the printout. The machine was not broken. The mathematics were exactly right. The only difference between these two futures was those 3 missing digits. What Lorenz had stumbled onto has a formal name: sensitive dependence on initial conditions. In an ordinary system, a small error stays small. Aim a cannon a hair to the left and the cannonball lands a hair to the left. But in a chaotic system, errors do not stay put. They feed on themselves and grow, doubling and doubling, until the tiniest uncertainty swallows the entire prediction. This was the real discovery, not that the world is random. Lorenz's equations were completely deterministic, with no luck or chance anywhere inside them. The shock was that a system could be perfectly deterministic and still be impossible to predict, because we can never measure the present with infinite precision. And in chaos, whatever we miss, no matter how small, eventually takes over everything. In 1963, Lorenz published his findings in a paper with the quiet title Deterministic Non-Periodic Flow. For years, almost no one outside meteorology noticed it. In it, he had boiled his weather down to just 3 simple equations describing a loop of rising warm air. When he plotted their solutions in 3 dimensions, something extraordinary appeared. The path never repeated itself, never crossed itself, and never settled down, yet it never flew off to infinity either. Instead, it traced an elegant double spiral, winding around one center, then leaping to another, back and forth forever, in a shape that looked uncannily like the open wings of a butterfly. This figure is now called the Lorentz attractor, and it captured the strange heart of chaos in a single image. The system was unpredictable in its details. You could never say which wing it would visit next. And yet it was bounded and ordered overall, always tracing the same beautiful form. Chaos, it turned out, was not the absence of order. It was a deeper, wilder kind of order. For years, the idea needed a name that would stick, and it got one almost by accident. In 1972, Lorenz was scheduled to give a talk at a science meeting in Washington, but he forgot to send in a title. So a colleague, the meteorologist Philip Merrilees, invented one for him. Predictability, it read. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The phrase was unforgettable, and the name escaped into the world. From that day on, Lorenz's discovery belonged to a butterfly. The first and deepest casualty of the butterfly effect was the weather forecast itself. If a rounding error in the 6th decimal place can rewrite an entire forecast, then no matter how many satellites we launch or how powerful our computers grow, there is a wall we cannot pass. For decades, scientists argued about where that wall stood. Then in 2019, a team led by the atmospheric scientist Fuqing Zhang at Penn State put a number on it. Using the two most advanced forecasting systems on Earth, the European model and the American Next Generation model, and feeding them a nearly perfect picture of the atmosphere, they found that useful weather prediction has a hard ceiling of about 2 weeks. Today, we reliably forecast around 9 or 10 days ahead. Zhang's work suggested that, with heroic effort, we might one day push that toward 14. But beyond roughly 2 weeks, the butterfly always wins. The atmosphere simply forgets where it started. This is not a failure of our technology. It is a law of nature, as firm as the speed of light. You do not need a whole planet to see this. You can hold chaos in your hands. Take a double pendulum, just one pendulum swinging from the end of another. Release two of them side by side, starting them as identically as a human possibly can, different by as little as 1/1,000,000th of a radian, an angle far thinner than a hair. For a heartbeat, they swing together. Then, within seconds, they tumble into completely different dances, and no one can predict which goes where. The same ghost haunts the heavens. The motion of 3 objects pulling on each other by gravity, 3 stars, or even just the sun, the earth, and the moon, is the famous three-body problem. Back in the 1890s, the mathematician Henri Poincaré proved there is no neat formula that can solve it for all time. Add a third body, and clean prediction collapses into chaos. It even hides inside living things. In mathematical models of animal populations, starting with 11,107 insects can lead to one future of booms and crashes, while starting with almost exactly the same number leads to a completely different one. Weather, planets, populations, traffic, even the rhythm of a heartbeat. Once a system is rich enough and feeds back on itself, chaos is waiting inside. Now here is where almost everyone, maybe even you, has the butterfly effect slightly wrong. The popular version says that a single butterfly, by flapping its wings, literally causes one specific tornado on the other side of the world. As a piece of physics, that claim is almost certainly false. The atmospheric scientist Roger Pielke Sr. puts it bluntly. The idea that one butterfly flap can produce a tornado thousands of kilometers away is, in his words, a categorical no. The butterfly was never meant to be a cause. It was meant as a metaphor. Bowen Shen, a mathematician who has spent years studying Lorenz's work, calls the butterfly effect a kind of Schrödinger's cat of science, an idea that has never been truly proven or disproven because it lives in the gap between metaphor and measurement. As another researcher put it, not all butterflies make a difference. Most tiny disturbances simply fade away, smoothed out by the larger currents of the world, the way a single whisper is lost inside a storm. The deep claim of the butterfly effect is not that everything matters enormously. It is that we can never know in advance which small things will matter and which will vanish without a trace. That uncertainty is the whole point. In fact, when researchers recently tried to train an artificial intelligence to reproduce the butterfly effect inside a weather model, the AI simply could not do it. It smoothed the chaos away. The butterfly, it seems, is harder to capture than we ever imagined. Strangely, humanity sensed all of this long before we had the mathematics for it. Centuries ago, a proverb warned of exactly this kind of cascade. For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. And on it goes until, for want of a single horseshoe nail, an entire kingdom falls. In 1952, years before Lorenz, the science fiction writer Ray Bradbury wrote a story called A Sound of Thunder, in which a time traveler steps on one prehistoric butterfly and returns to find his whole world quietly, chillingly changed. And in 1985, Back to the Future built an entire blockbuster on the same nervous idea that one small change to the past could unravel everything that came after. We have always suspected that the world hangs by threads we cannot see. Lorenz simply proved it with numbers. So what does the butterfly effect really leave us with? It is the quiet end of Laplace's demon. The universe may truly be a machine, every gear turning by exact and unbreakable law, and yet that very same machine can be permanently, mathematically unpredictable, because no one, not even that imagined godlike intellect, could ever know the starting point exactly enough. Determinism and unpredictability, it turns out, can live together in the same world. And this is not only about weather. The same sensitivity runs through economies and ecosystems, through the spread of disease, the beating of the human heart, and even the turning points of a single human life. It means the future is not a fixed script waiting to be read. It is something far stranger. Lawful, but open. Shaped again and again by causes far too small for anyone to ever see coming. Edward Lorenz set out to predict the weather, and instead he discovered the limits of prediction itself. A coffee break, 3 missing digits, and a butterfly drawn in numbers. So the next time someone tells you the future is certain, remember the tiny flap that no instrument can measure and the storm that no one can foresee. If this changed the way you see the world even a little, well, that is a small cause too. Follow along and let us see where it leads. Thanks for watching.